The second segment of the video clip that I'm doing for chapter 19. I already solved this problem but did not use any planes of symmetry, so I would like to do that right now with an assembly. This assembly is made of the vertical cylinder, horizontal plate, and left column and right column. Once I do this, I will prepare another video segment where this problem is not going to be solved as an assembly, but it will be solved as a single part. Now, if you have a problem which requires a hybrid analysis, I leave it to you to decide whether you want to go the direction of the assembly approach or part approach. It's entirely up to you. But presently, it is an assembly. So let me go actually pull out that assembly that I saved before cutting, and that was from the first problem. Let me see if I can find it. One plane of symmetry. Okay, there. So there is my product. What I'm going to do is I'm going to use the split. While here I'm in the assembly design, I'm going to use the split, the saw, and select the middle plane. And it says when you do this, these parts are going to be affected. I say fine. Let me see. Some affected parts may have bodies that does not contain any solid. This may cause an update error. So that's okay. Let's see what happens. All right. Oops, it doesn't like it. Okay, so it did actually. Oh yeah. So it did. Sorry. So this saw is cannot be used to cut the plate or the shell or the surface and these lines. So let's go ahead to the wireframe and surface design. Let me go to this part, we're in wireframe and surface design and use the split. Now, okay, so this is the other, we're going to keep the other side. Very good. Okay, that's fine. All right, so this thing, this guy is not actually even needed when we do the analysis. Okay, we don't have to mesh it, therefore it's not going to bother us. Okay, so let's go back to the assembly. There we are, and then we're going to go to generative structure analysis. Okay, fine. Let me change the rendering here. All right. First of all, the solid is mesh automatic. This shell we have to mesh it ourselves. And where is the shell mesh or octave triangle mesh? Right there. And I'm going to make that point 0.1. There we are. And just give it a thickness. Where is the thickness? 2D property right there. I'm going to use the same thickness as before. This has to be solved with or meshed with beam elements. So let's go ahead and get the beam measure right there. All right, and give it a cross section. So there's the cross section, rectangular. The dimension is 0.1 by 0.1. You see that exactly the same information that we were using before. Now we cannot close this thing because the cross section is rectangular. If it's not circle or tube, you cannot close it. So you need to select an orientation point. And if you look at it, this orientation is kind of weird the way it is. But if I select the orientation point, it turns it and it puts it exactly the way I wanted before. Now, it is true that this line is here, but that line was not meshed. Okay, was not meshed. So if I say show me the mesh, notice that only the beam elements there, shell elements here, and the solid are shown. Let me change the color just so that it looks like the previous case. So I'm going to make this thing yellow as I did before. And the beam, there's only one of them. The other one is not. The other side is not mesh because I don't need it. And let's see now. Properties, graphics, and we make it green. There we are. It's exactly the same setup as before. Let me deactivate this. And this is, if it's bothering me, I can always hide it. Okay. Now save the analysis file. Save management, analysis, save as. Let's see now, one plane of symmetry right there is going to go there. Okay. Now let us create our restraint. So the top of this beam right there, it is clamped. The bottom of this is also clamped. We have this face, the face of the solid object surface slider. See that? And these two edges, these are edges associated with shell structure, so I cannot use surface slider, I have to use user-defined restraint. And let's uncheck everything. So this edge and that edge happens to be in the XZ plane of symmetry, right there. You can look at the coordinate system, XZ plane of symmetry. As soon as you say XZ plane, there is no displacement in Y, and rotations are opposite. Okay, good. Now we have to create a connection between the end of the line and the vertex associated with that corner. So let's see now, general analysis connection. So let me hide this plate. So right there. And for the second component, I am going to bring this thing into the show mode. Hide the line. I still cannot select this vertex, so I'm going to hide this white dot, which is actually the connection that was created right there. All right, and I'm going to call this thing right column and plate corner, or something like that. Corner. Actually, vertex is the more appropriate way to call it. Okay, good. Now, the other thing is that we need a connection between the surface of this solid object and the edge associated with that shell, because I'm assuming that these two are perfectly welded together. So connection for the first component, the surface of the solid object, I'm going to hide that. For the second component, this edge. Okay, and let me call this thing, this is the connection between the vertical solid, and a plate, horizontal plate. Okay, good. Okay, now when it comes to defining the nature of the connection, the one that goes with this corner, let me bring that guy into the show mode, and this into the show mode. This connection must be rigid. When it's vertex to vertex, CATIA demands that it be rigid. Okay, so I'm going to select OK. You can either do it from here or from the screen. So right there, see that? And I'll talk about this transmitted degrees of freedom later on. And then the other one must be welded. Welded means that in CATIA's language, it's going to be fastened. It puts a fastener sign there. Okay, and then we apply a pressure. The pressure, although we're taking half of the stuff, it doesn't change because pressure is pressure. Whether you take the entire surface or half the surface, then it doesn't matter. All right, so let's run. Well, first of all, save everything, and then we're going to run it. Where's the run? Right there. Hopefully we didn't forget anything. Don't worry about the warning message. It's saying that solid elements do not have rotational degrees of freedom. Okay, very, very good. So let us now look at the deflection. There we are. And you can animate it. And this is exactly the same pattern that we had before. If you look at the displacement, let me change it to average ISO and material shading. Everything displaces. For example, if you want to see the displacement of the solid, double click on it and select the cylinder. That's this. You can see that. And these are the displacement associated with the solid only. If you want to see the beam, so don't show me the solid, show me the beam, which is, let's see now, let's find the beam. Oh, 1D mesh, that's what I want. Okay, right there. Now this drawing is may not be completely correct, because although the shape is correct, because I wonder what the beam look like. Linear, yeah. Yours may look different from that. I'm sure this has something to do with my graphics card. It should not be like that. Okay. Now let me show everything once again. Notice that this beam is bending. You can see that. This column is bending. So let us say that this was actually a cable. Let us say this was actually a cable. It was not a column. So what you do to turn it into a cable, obviously cables do not bend, they just stretch. So you go to properties, and this is the rigid property that I made. Remember I said I'm going to talk about these transmitted degrees of freedom? You click on it and it says, okay, what do you want to be transmitted between the cable and the plate? Well, if it's a cable, rotations will play no role, because there is no bending. And now run it again. I unchecked it. Run it again, and this is going to go straight down, and it will not bend. Let's try it. Where is the deflection? Right there. And let me get everything. Show me everything. It's already shown, and yeah, you can see that. So let me change this thing to average ISO right there. You see, it does not bend. It just goes straight down if it's a cable. So at least I showed you in the event that you don't have a column and you have a cable, how to model that. Now, unfortunately, cables in CATIA cannot go under compression, because they don't have any stiffness under compression. So hopefully, if you have a cable, it's always under tension. Is there anything else that I want to do? The answer is no. The third video segment, I'm going to do this exact same problem, and I will use symmetry. I will not use symmetry, just like it's done in the book, but I will not be using it as an assembly. I will not be doing it as an assembly. I make everything in a single part. And as I said on the test, I leave it to you to decide whether you want to go the assembly route or a single part route. As long as you solve the problems we're asking correctly, it's entirely up to you.